All right, are there any questions before we get started? Did we think of any? Good to go? All right. Let me pull up my notes. So yeah, last time on these slides, we don't have much more to do. I just want to talk about binary just briefly a little bit longer. So we were talking about new bases. Binary. What in the world is that? Ones and zeros. Our numbers, remember, are decimal numbers, base 10 numbers. We have 10 digits total. Before we run out, if we try to add 1 to our last digit, 9, we have to add a new place, the tens place. So that's 123 base 10. Binary is base 2, so you only get 2 digits. And like base 5, you only get 5 digits, things like that. A bit is called, stands for a binary digit. That's a 0 or a 1, because you only get those to be your digits in binary, self-explanatory. And then finally, a byte is any 8-bit binary number. Could be starting with a bunch of zeros, could be very small still, not a problem. Okay, so yeah, this is a decimal number, I'll use the subscript, and this is a binary number, base 2 versus base 10, they're not the same. Well then, what is this number in decimal, you may be asking? Let me teach you how to do that. Let me show you how to go from binary to decimal, okay? It's very, very easy to do that. You just do the, what's this called? It's called an expansion, but I forget the word that comes before the word expansion. It's some kind of expansion of this number. Remember how to do this from grade school? 1, 2, 3, 4, 1,234. That's, well, it's, the first thing we learned how to do was like, it's 1,000 plus 200 plus 30 plus 4, right? And then we broke this down further once we learned about powers. Like it's 1 times 10 to the 3 plus 2 times 10 squared plus 3 times 10 plus 4 times 10 to the 0. Secretly, that works because it's 1. Anything to the 0 power is 1. That's the 1's place, the 10's place, the 100's place, the 1,000's place. The trick is this still works for binary. You just change the base. You see where the base appears? Like this is the 1's place, the 10's place, the 100's place, the 1,000's place. If you just replace that with 2 instead of 10, you can translate any binary number into decimal. Just do your normal arithmetic, and this ends up giving you what you think. Okay, so this, for example, what is this number in binary? How do we convert it to decimal? Well, it's just 0 times 2 to the 0. You work from right to left, right? 1 times 2 to the 1 plus 0 times 2 squared plus 0 times 2 cubed plus, finally, a 1 times 2 to the 4th. See how I'm doing that? 1 times 2 to the 4th. And you can get rid of the zeros, and it just expands to 1 times 2 to the 4th plus 1 times 2 to the 1st, which is 16 plus 2. This number in binary is 18 in decimal. Okay? So you just use that same kind of expansion, changing the base this time, and do your normal decimal math that you know how to do as a human, and you'll end up with whatever decimal number that binary number represented. Okay? Any questions about that kind of expansion? Does that make sense? In that case, I'm going to make this, I'll put this like right here. I'll screenshot it. I want you to try. I'll give you 2 minutes. This is the largest 4-bit number, 1111. Please figure out, using this strategy, figure out what 1111 in binary must be. What number is that in decimal? Okay? So please help each other in your groups, and then we'll come back and discuss. So it'll take about 2 minutes to try this, 2 minutes to do your math. You remember your powers are 2? What is that? All right. Did we get it in time? You don't have to shout out your answer if you're not super confident, but let's break this down. Well, you always start with the rightmost digit. That's 1 times 2 to the what? What's that rightmost digit? That's 2 to the 0. Just like the ones place is 10 to the 0. Plus another 1 times 2 to the 1. Plus 1 times 2 to the 1, or 2 squared, sorry. Plus 1 times 2 cubed. Let me draw that slightly better. There we go. So if we add all those together, that's going to be 8, sorry. 8 plus 4 plus 2 plus 1, which is 15 in decimal. That's the final answer. Did we get that? So the largest 4-bit number, 1111, is 15. It's cute because it's 1 times 2 to the 4 minus 1. Think of how those relate. All right. Any questions about that before I move on? Because the other direction, going from decimal to binary, is the harder direction. So I want to make sure we got this way down. All right. So to go the other way, to go from decimal to binary or to any base, you have to repeatedly take remainders, which is weird, a weird idea. You have to repeatedly take the remainders of numbers after dividing by something, and then also just doing division and chopping off any decimal places. So here's an operator that we will eventually learn in Python, but here's how you do it. It's called the percent operator. It stands for modulus. That performs division and gives you back the remainder. This is called the modulus operator. So what this does is it divides by 10. You can think of this like there's kind of a slash in there, right? 1, 2, 3 divided by 10. But it doesn't give you back the division result. It gives you back how much is left over after the division. It gives you back the remainder. Okay? It's called the modulus operator. So this is going to give me back 3. Kind of cool. Because if you divide 123 by 10, you get 12 with 3 left over, right? 12 remainder 3. So the answer is 3. Remember that kind of division? 123 divided by 10 is 12, remainder 3. So it's giving you back this part, not remainder. That 3 without the fraction involved. Okay? So I hope that makes enough sense. Please yell at me if it does not. But that's going to give us the way that we can extract digits. Okay? Because that's what we really want to do. We would like to extract the binary digits from a decimal number. So let me show you how to extract the decimal digits from a decimal number. That's the easier way. And then we'll show you how that all corresponds and it all still works out if we change the base. Okay, so here, let me show you an algorithm to extract the decimal digits from 123. So I want to get out the 1. I want to get out the 2. I want to get out the 3 as well. Okay, let me show you how to do that. If you didn't know what the number was, it was a black box, and you can only divide and perform remainders. Okay, so look what happens. We can always get the rightmost digit by dividing by 10 and taking the remainder, can't we? 123 modulus 3. I say mod for short, to say that short. That's a common abbreviation. So 123 mod 10 is 3. And that gives me that rightmost digit. Cool. That'll always work. You can always get that rightmost digit. And then, because now I know how to get the rightmost digit of any number, it would be really nice if I could transform 123 into 12, right? Oh, I can do that too with just normal division. Ooh, okay. So let's convert 123 to 12 by dividing by 10 and throwing away the remainder. Okay? That's the idea. And once we get to 0, the algorithm is completely extracted all digits. So you get them in reverse order. Let me show you this. You start with, what's the rightmost digit of 123? 123 mod 10. That gives me 3 back. It goes in 12 times with 3 left over. And then, to shift away this 3 and to give me 12 so that I can get its rightmost digit, I will do division and chop off the remainder. Divide by 10, or 123 divided by 10. That gives me 12, because we throw away the remainder. Throw away the remainder. called integer division for those of you who have programmed before, right? And then now we have 12, and I can get the rightmost digit of 12 very easily by doing mod 10 again, right? 12 mod 10. Let me draw that better. 12 mod 10. That's 2. Goes in once with 2 left over if you divide by 10. And then let's shift away that 2 so I can get the rightmost digit of the number that comes to the left of it. 12 divided by 10, throw away the remainder, is just 1, right? Then I can get the rightmost digit of 1, 1 mod 10. Well, 10 goes into 1 0 times with 1 left over. There's the digit. And then, all right, let's shift away the 1. Let's see if there's anything else to do. Any more rightmost digits to get. 1 divided by 10, throw away the remainder. It goes in 0 times. And so that, once you hit 0, you know you're done. And every time you took a mod, you performed the modulus operation. You got a remainder, you got a digit in reverse order. So you got the rightmost digit, then the second rightmost digit, and the third rightmost digit. So the answer is 123. 1, 2, 3. I got all the digits in order. Reverse order. Okay, so that's the algorithm to extract decimal digits from a decimal number. Does that make sense? That is new, but hopefully not too horrible. Because look where the base appears. There it is, there it is, there it is. Every time I'm doing mod or division by 10, if I want a decimal digit back. So that implies that if I want a binary digit back, I want the rightmost binary digit, I want to shift away the rightmost binary digit, I could just change these 10s to 2s. And that really will work. So let me show that to you. Here's how you can convert from decimal to binary. So repeatedly extract the rightmost digit in binary with mod 2, and then shift that bit away by divide by 2. So let me show you how to translate 8 in decimal to binary. We're not sure what it is. So you always get the rightmost digit by starting with the number and taking the modulus by 2, by the base you're trying to convert to. So this will get me the rightmost bit of 8 in binary. And the answer is 0 because 2 goes into 8 cleanly with nothing left over. So the rightmost digit is a 0. Then I want to shift away that 0 by taking 8, dividing by 2, and chopping off any remainders if there are any. There's none, so I'll just take the 4. So now I want to convert 4 to binary, get its rightmost bit. 4 mod 2. Again, goes in cleanly with 0 left over. The next digit is a 0 then. Shift away that 0 by dividing 4 by 2. That gives me 2 again. All right, get the rightmost bit of 2 by doing mod 2. Again, it goes in cleanly with nothing left over, no remainder. Let's shift away that 0 now. 2 divided by 2. Chop off the remainders. Okay, that's 1. Get the rightmost digit of 1. 1 mod 2. Sorry, I ran out of room. How about, there we go. 1 mod 2. That's 1. And then I want to shift away that 1 by doing division. 1 divided by 2. Sorry, it's so small. Nothing left over, that's 0, so I'm done. And every time I took a remainder, I got a digit in reverse order. So it's 0, 0, 0, and 1, but backwards. So the answer is 1, 0, 0, 0, base 2. That's the answer. Does that make sense? And you can always check this by going the other way now, because it's what? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3's place. 1 times 2 to the 3. Hey, that's 8. Any questions about that process? That will work to convert to any base. All right. So let me give you this, and now I want you to try it. So please help each other out. Please try to convert 25 to binary using this process. Help each other, and I'll give you 3 minutes for this one. Please yell at me if you have any questions about anything. If you'd like to cheat and you forget how to do mod 2, like you don't know your remainders, just use a calculator. If it's 0.5 in the answer, that means there was 1 left over, right? If it's 0.0 at the end, then there was nothing left over. There can only be a remainder of 1 or 0 when you divide by 2. That's perfect. That corresponds exactly to the binary digits that we could get. About 30 more seconds. All right. Let's see if you got what I will get. Remember, you can always check. You know how to go the other way too. So you can immediately check your answer. 25 in decimal. What is that in binary? Well, let's get the rightmost bit. 25 mod 2. That's an odd number, so the answer is 1. Let's shift away that 1 in binary by dividing by 2. The answer is what? 12.5, but we dropped the remainder. So it's just 12. Now I want to convert 12 to binary. I want to get its rightmost digit. Rightmost bit. 12 mod 2. Well, that's even, so it's 0. And then 12 divided by 2. Let's shift away that 0 in binary. Get the next number I need to convert. That's just 6. 6 mod 2. Again, even, so 0. Let's shift away that 0. 6 divided by 2, that's 3. Let's get the rightmost bit of 3 now. 3 mod 2 is 1 because it's odd. 3 divided by 2 is 1 because you dropped the remainder. And let's get the rightmost bit of 1. 1 mod 2, that is 1. 1 divided by 2 to shift away that 1 in binary. See if there's anything left to do. The answer is 0, so we're done. So every time we took a remainder, we get an answer in reverse order. So it's 1, 1, 0, 0, 1. Okay? 1, 1, 0, 0, 1. That is the binary representation of the number 25. Is that what we got? Nice. Pat yourself on the back if you did. If you want to check that quickly, remember that this is the, what is it? 2 the zeros place. So this is 1. If it's a 1, this is 2. If it's a 1, 4, 8, 16's place, right? So this is 16 plus 8 plus 1, which is 24 plus 1, 25. That checks out. Okay? So that's how you can check yourself quickly on a test or something. But that is the harder direction. Does it make at least a little bit of sense? Any questions about it before we move on? All right, now you know how to do cool stuff with binary. Let me show you how arithmetic works. It's exactly how you would expect. You just have to carry a lot earlier than usual. So here are 2 binary numbers. Let's add them together, whatever they are. Okay? This is 1 plus 1. In binary, that's 2, right? I don't have a digit for that. I need to carry. The answer is 1, 0, right? That's 2 in binary. 1, 0. So it's 1, 0. This rightmost digit is a 0. Again, I have 1 plus 1. The answer is 1, 0, so I have to carry. That's 2. Now I have 1 plus 1 plus 1. Oh, man. That's 3. Again, the answer is 1, 1 now. That's 3 in binary. I got to carry the first one. Again, 1 plus 1 plus 1. That's 3, so 1, 1. Boop, boop. Just like that. So that's the answer. And you can quickly check, did this do the right thing? This is 8 plus 4 plus 1, that's 13. I think, yeah. And then this one is 15. We've done that one now. 15, base 10, base 10. And the answer is supposed to be 28, base 10. Does that work? 16 plus 8 plus 4. 24 plus 4 is 28. Yeah, seems to be right. So that's how you add binary numbers. You just have to carry a lot sooner. But it's very simple because the answer is either 1 or 0 at the end. And you carry as much as you need to. Any questions about that? All right. Yeah, I'm almost ready for the next set of slides that I want to do today as well, something slightly different. And then I have also, right, a new essay to release today because you have one due. So don't let me forget that. So just to bring it all together, like why in the world am I teaching you this? This is kind of how a computer is made. How in the world does your computer actually do this stuff? Let me bring it all together just for fun, okay? If you look at the exclusive OR operation, it's really doing one bit addition, isn't it? Because one exclusive OR with 1 is 0. 0 exclusive OR with 0 is 0. And all these ones in between, 1 exclusive OR with 0 is 1, 0 exclusive OR with 1 is 1. That's addition in a single bit. This one's got a carry, right? But the answer is 0. This one, answer 0 and there's no carry. It did one bit addition, exclusive OR. What? So that means if you chain a bunch of exclusive ORs together, you can do addition on any binary number as long as you need it to be. You just need to remember the carry as well. You know that you need to carry if the two numbers are both 1, right? And that's A and B. And gives you whether or not it should be a 1, right? Because it's 1 only if they're both 1. Isn't that cute? And so you can add a bunch of numbers. You can chain a bunch of these adders circuits. So here's your 2 bits you want to add. The output for the sum for that single bit is exclusive OR. That's the exclusive OR gate. And then to see if you need to carry, and you'll chain that to the next bit that you need to add, you just AND them together. Isn't that so fun? I don't want you to memorize this or anything. It's just really cool. And then once you have carries involved, you have 3 bits to add at most, right? You have your current 2 bits that you want to add together, and then you have optionally a carry, a 3rd bit. So you have to add that as input. So you have a carry in and a carry out now. So you just do a couple exclusive ORs to get the sum on those 3 bits for your final answer for that particular bit. And then to see if you need to carry out, it was just, hey, we're 2 of them 1 in any of the directions. So you do some ands and you OR them together. But that's the gist of it. Isn't that cool? We can do addition in a computer with a bunch of these little circuits. So that's the point. Okay, yeah, go for it. Oh, nice. So, yeah. Isn't that fun? Any questions about that before I move on to something completely different? So, yeah, this is what a computer is doing. It's just a bunch of these gates that you've learned about doing this kind of stuff to add numbers, among other things. All right, so that's the first set of slides for the day. The next one's a bit more philosophical. I want to talk about privacy and encryption. Why not? All right, so let's first talk about privacy, because it's a little bit different than it used to be, right? Now that all of our phones are connected to the internet, everything's interconnected, maybe we have a little bit less privacy than we used to, right? Got microphones all over the place. So let's see what that means. Let's try to unpack it all. Okay? Let's talk about the Constitution, I guess, first, because that's kind of like the ultimate law, right? So let's talk about that. What it does, the Fourth Amendment to the Constitution prohibits unreasonable searches and seizures. That's a very generic word, unreasonable, so that can be manipulated to what you want it to be, maybe. But at least we've kind of like come up with the idea that if you want to like search somebody's house, you need a warrant and you need probable cause. Okay? You can't just go walk in as a cop and just go search somebody's house. You need a warrant. So that's quite nice. That means our house is safe, more or less, from unreasonable searches and seizures. But the internet is not a house, right? The internet is a weird place where everyone's connected to everybody else. It's like it's one big house. I'm in it, you're in it too. Can you search through your own house? Question. So it's a little bit different, and we should maybe change our rules for the internet. Maybe it's treated differently. Let's see what's happening. What's happening in law? Okay, so let's apply this to phones first. So back in the day when phones first came out, that was like the original way of like doing something to sneakily see what somebody's up to. The Supreme Court originally ruled that you did not need a warrant to tap a phone because they said that the conversation was not a tangible object. You can't touch it. Therefore, it doesn't matter. You don't need a warrant. You can just listen in on the phone lines. Interesting. But in the 60s, they changed their minds, and so they're allowed to do that. In this case, at least, it was for the better. But that's kind of like the protection that we have right now, okay? Just in our houses, with phones, with old technology. How does this translate to the present day? Let's see what other things are happening. Let's see what other companies are doing, in fact. So this is a fun little story that you'll read about if you bought the textbook. Oh, let me fix that. Why in that? This has happened before. Was it during this class that it happened last time too? Please try to connect again. Glad that I caught it this time. There we go. That makes no sense at all. Let's talk about Target. We all love Target. I sure do. Target caught some flack for doing something that is kind of commonplace now, but let me walk you through the story. So Target was doing some data mining on their customers and their purchase habits. So if you've never heard this fancy term before, data mining, it sounds really cool. All it is just you have a bunch of information and you're trying to search for patterns in that information. So it's essentially glorified pattern matching, pattern finding. And as a corporation that sells things, they kind of want to do this, right? So that they can send you stuff that you might be interested in, and then you give them more money, right? So that's what Target is good at. But here's what they did. They noticed that if you're pregnant, you tend to buy certain products at certain stages of pregnancy. With enough data mining, they figured out that. How they matched that to pregnancy stages, I'm not sure, but they managed to. And so they took that data and they sent targeted coupons, I love that, to the women who were pregnant, and ads for things that they're probably going to want to buy soon, okay? And so that, to a lot of people back then, was not a good thing. Like, that is a privacy infringement, maybe, right? How dare you try and think about what I want? How dare you use this information about me to give me more personalized ads? I didn't want them in the first place. Okay? So the question is, does this infringe on the privacy of someone who is pregnant? And so you can always ask our boys about this, but I'm sure you have your own opinions, and maybe you can use their opinions to motivate your own. So I think Kant would ask the question, like, should everyone always do this? Should everyone always try and mine as much data, try and sell people things that they're interested in, shove these ideas down somebody's throat? And I think the answer would be no from Kant, because he's all about treating people not as means to an end, not as means to a profit, but as humans. I don't always want to be thrown ads at every time I walk out the door or walk into a Target. So I think Kant would say, no, this is a bad idea. Okay? And then the utilitarians, of course, Mill et al., would be like, is there any utility in this? Who wins? Who gets more about? Who gains the most? And you have to weigh this. So you've got Target on one end, you've got pregnant people on the other end. What is going on there? So maybe, as a utilitarian, you might agree that this is a good thing. Like, maybe if you're pregnant, you are not noticing all these coupons that are out there. You're a little busy. And so you're going to save money if Target's going to notice these things that you need and send you coupons and ads, because you're going to buy them anyway. And so maybe there is some good utility in that. But then there's also, on the flip side, some privacy issues. Like, they shouldn't have access to my purchasing data. I don't want them to have that. And so maybe you could also argue that utilitarians might say no to this. It's a bad idea. But there's a weighing going on from a utilitarian perspective. Does that make sense? You remember those two schools of thought? That's a fun idea. Target's allowed to do this, that's for sure. They're not, this is not a protected right of anybody. Your purchase history at Target. That's kind of cool. Stop me at any point if you'd like to discuss this. I just have a bunch of examples. That's my idea. So, next is ad blockers. This is the ad blocker that I use. I am a big fan of them. It's hard to read an article on a website without them these days. So here is the scoop about ad blockers. It's not illegal to block ads, which is nice. But technically, it's illegal to block ad blocker detectors on websites. That's a mouthful. So you're not allowed to block ad blocker detectors on websites because they sometimes make money from that, okay? The argument is you're tampering with access control, and websites should have a right to control access to their content that they have copyrighted, like a news site, for example. You've probably been to a site and they're like, if you have an ad blocker, and they probably said, oh, please turn your ad blocker off. We have detected that you have one. And the reason they're not just showing you the article without any ads, the reason your ad blocker is not blocking that detector of the blocker is because of this, which is fun. So yeah, websites have a right to control access to the copyrighted content that they produce, sadly. And so then maybe you're kind of forced to use that website with ads because of it. Okay? So again, you can ask the question, is this a good idea? Should we have ad blockers on the internet? And Kant might ask the question, should we always look at or click on ads? Should we always buy the products that are being offered to us? Right? He would have that word always in his questions. And I think that the answer, at least for those, if you frame it that way, is a resounding no, right? Why in the world would you want to do that? I'm not going to click on every ad I see. It's not my job to do that, yes? So maybe ad blockers are a good thing. Kant would probably agree with them. There's no need to look at all these ads if I'm not going to click on them anyway. And then Mill, a utilitarian, would always ask, what are the benefits? What's going to happen here? So I guess there's two sides to this coin as usual, and you'd have to argue what you're in favor of. But a utilitarian might say, yeah, I think ad blockers are great because I, as a consumer of this content that has no ads now, I can see exactly what I wanted to see. There's more real content on the page. I don't know why, but I really hate the word content. I'm sad that I have to say it a lot today. There's more real content on this page because all the ads are gone. Now I can suddenly read the article without getting lost. I'm sure you've been on a few websites that do that, like the Fresno Bee. If I look at that on my phone, it's horrible. So many ads. The flip side to this is, well, the reason that you would like to have ads, the reason that the website has them in the first place is because they make money from them, right? By showing those ads on your screen, they make a tiny little bit of money for every ad that's shown, as well as they make a little bit more money if you click on that ad. Okay. That's the whole point of advertisement, right? So if you block them, the website itself gets less money. That's the flip side. So maybe it's better to turn off your ad blocker, especially for the websites you care about and want to fund. You want them to stay funded, yeah? So that is the downside to blocking ads. And here is my favorite ad blocker, uBlock. So, yeah, any questions on this? Do we have strong opinions like I do? Maybe not. I just have a bunch of little examples today, and then I'll send us off with our new essay. All right, last example for this little section of the slides. Let's talk about Street View. This is quite interesting because I love Google Street View, right? It shows me exactly what the building's going to look like when I'm going there and I've never been there before. Like, I know where the parking is. I know what it looks like on the outside. I'm not going to miss it now. A lot of countries agree. Like, they love Street View. It's not illegal. They don't care that Google's driving a car around with a 360 camera, taking pictures of all the streets. But some countries disagree with that idea. Not everybody holds the same views on privacy. They're not all set in stone like you might think they are. Google Street View, for example, exists pretty much everywhere, especially in Europe, except for Germany. This is a screenshot of, like, it's blue if there is Street View. You can see that there is not a lot of blue in Germany except for, like, major cities where they can get away with driving a car around, like, public roads and things like that. But Germans tend to care about their privacy a little bit more than their neighbors. And they have laws that reflect that. You're allowed to take your house off of Google Street View, for example, in Germany. It's very easy. You can click something and do that. Okay? And so this is quite different from the rest of the Western world and the US. What do we think? Would we rather be more like Germany? Should we make a law that disallows that kind of driving a car around streets leading to my house? Yeah, maybe the option is the right way to go. Something that Google does do for privacy purposes is they gray out, they blur out everybody's face, right, in the Street View images. They blur out everybody's license plate number. Sometimes they don't get it perfectly right, and you can, like, click something to have them go and fix it. But they do try their best. But the Germans didn't want it in the first place. That's a cultural thing. That is just as valid as us wanting it. So, yeah, that's food for thought, I guess. We could have a fun discussion there if you'd like. But, yeah, if we're good to move on, the next thing that I want to talk about is encryption. Because that's one way to remain private on the internet, right? To encrypt all the things that you're sending to Facebook, to Instagram, all those things. So let's talk about encryption. What is that in the first place? Never heard the word before. Encryption is just you're sending encoded information. The process of encoding that information and getting into a form that only the person you're sending that to can understand. Okay? Only the parties a message is intended for are supposed to be able to decode or decrypt the message. Okay? So you got encoding, decoding, and there's a concept of a message that you want to send. That's usually the metaphor. Okay? And so encryption is all over the place today. Its uses range from just security, like you're logging in on your bank account's website. You want to make sure that, like, Comcast or anybody sniffing in on your internet traffic is not able to view your password or your bank statement or anything like that you're looking at, as well as commerce, like you're buying something on Amazon. You're entering your credit card information. You want to make sure that only Amazon is the one getting your credit card number, right? So that's what encryption is good for, just making sure that as your data travels across the internet, nobody's peeking at it. Okay? And every website, Canvas, for example, this class website, for example, I'll stop the attendance soon. It's always HTTPS, right? That is secure HTTP. You can click on the little lock and it's like connection secure, and here's why. You are securely connected to the site verified by Amazon. Interesting. More information. Whee. So connection is encrypted with this very fancy kind of encryption. And you can look more into that. You can view the certificate of the website. Whee. Apparently, this is the real website that we're connected to. It's not just canvas.com. It's from the US. It's hosted on Amazon servers, things like that. This is all the fancy encryption information that's being used. I don't care that you understand any of this. I'm not going to teach it to you anyway. But this is the kind of stuff that ensures your privacy over the internet. And I encourage you to look up some of these words if you're interested. A lot of acronyms. There's like a hierarchy of trust as well. It's very cool to think about. But yeah, those are the uses, and they just make sure that everything is only, your secret stuff is only going to the places that you want that secret stuff to go. Okay? So let me walk you through different levels of encryption. Back in the day, back in the Roman era, I guess that's why they call it the Caesar cipher, they made up this kind of encryption. It's called this as well. I don't know how you pronounce it. I'll call it ROT13, I guess. It's short for rotate, though, so maybe it's ROT13, but I'd rather say ROT13. Here is this encryption scheme. It's very breakable, but back in the day, it was a very simple one, and maybe the other warring tribe that the Romans were fighting were not able to decrypt it. So this is how you do ROT13 encryption. You take whatever you're trying to send. Here's your message. Maybe it's hello. And you just shift it. You shift every letter by 13 in the alphabet to the right. Or to the left because it's symmetric. But and then when you wrap around, you just keep going. So like A maps to N, B maps to O, M maps to Z, and then N goes back to A. That's the idea. It's just 13 later, and you wrap around if you get out the end of the alphabet. After Z comes A, and vice versa. So that's quite nice. So like A plus 13 becomes N, B plus 13 becomes O, O plus 13 becomes B again. So it just wraps around, and that's why they did 13, because there's 26 letters in the alphabet. This encryption scheme is its own inverse, which is kind of cool. So if you add 13 to N again, you get back the original A. So that's pretty cool. So you do ROT13 once. On hello, you get Uryib, and that doesn't look like hello, really. That was encrypted. But then if you do this process all over again, because it is its own inverse, we say, you'll get back to hello. Isn't that cool? So that's a very simple kind of encryption, and it's called the Caesar cipher, ROT13. Are there any questions about that? So this is short for rotate. Rotate. 13 letters at a time. And you can do a different one. You can be like ROT7 if you would like. That's a very simple kind of encryption. Let me show you a fancier kind of encryption, because this acronym was on Canvas. This is one of the things that is keeping Canvas safe. TLS ECDHE RSA. There it is. RSA. I'm going to teach you RSA. Just briefly, though. It's very fancy. If you want to learn more about this, you have to wait until CSCI 26. So this kind of encryption is very cool. You have your message, and then you have what's called a key. 2 keys, in fact. There is a public key and a private key, which is kind of weird to think about. You have a key, your public key, that is just available to anybody. You tell them that. Here's my public key. I'm going to use that to sign my messages. That's the way that the lingo works. So you give everybody out one of your keys, okay? Anyone can send you a message using this public key, okay? So if you would like to send somebody this cloud of a message, you figure out what their public key is, and you sign your message with that key somehow. And that makes it encrypted, okay? So it's very mathematically fancy that this works. It was invented back in the 70s, and a lot of things invented back in the 70s are now obsolete. RSA is still in use because it's so cryptographically secure. Okay? Then there's the other kind of key. There's a private key that lets you decrypt the messages that were sent to you using your public key. Okay? So here's the idea. Here is, I don't know, you. Here is the sender who wants to send you a message far away. They take your public key, they send you a message encrypted with that public key. And that renders the message into a form that is unintelligible to anybody else except the person with the matching private key, which is pretty cool. So before they send you a message, they have to, maybe I should draw this second. Before the sender sends you a message, they have to ask you for the public key. And so you have to give that to them. It's like, hey, here's my public key. Or they look it up on the internet because it's freely available. And so now they have that little key. They'll use that to encrypt the message that they send to you. So a little envelope with a key on it. Okay? And then you are saving secretly to yourself a private key. And keys are just fancy long numbers. We'll get into that in the next slide. That will unlock the message, and you can read exactly what the sender was trying to say, and they encrypted it. Nobody else could see that encrypted message. They couldn't break it. only you with a private key can unlock it. Okay? And this is all about numbers. A message is just a number, just a long binary number, right? A public key and a private key is another just long number. And I'll teach you that on the next slide. But the reason it all works is because it's very, very hard, at least for non-quantum computers, to factor numbers. There's a lot of large primes involved in RSA. And factorization is the bottleneck. So if you use large enough prime numbers, not even like the fanciest government with all of their supercomputers can hack your key for a very long time. Really cool. Okay, so yeah, let me teach you RSA. It's a fun little thing, and then we'll keep on going. So again, I don't want you to like memorize any of this stuff. Just look it up if you're interested, and I'm happy to talk more about it. That's just something I want you to know about, to be more digitally aware. So first of all, RSA uses modular arithmetic. I just taught you what the modulus operator is. There's a lot of calculation of remainders involved, just for very large numbers this time. And your public key that you give to other people is secretly really two numbers. It's a number n and a number e, that we'll get into in a second. And then your private key is just one single number d, okay? All three of those, n, e, and d, are generated from two giant prime numbers that are hard to figure out what they were. And D and E are called modular multiplicative inverses for a reason that will make sense in a second. And here are three small versions, a very easily hackable public key and private key, but good for discussion. Okay. Usually these numbers are several tens of digits long. Okay. Over 100 digits usually. So yeah, first of all, D and E are modular multiplicative inverses, and they're hard to find those just by guessing. So if you have some number that is your message, because everything that you're sending is just a fancy number, if you take it to E and then take it back to D, you end up with M again. That's the secret. They're like inverses of each other. They cancel each other out in a certain way. If you do mod n, because these aren't really inverses, you're not going to get fractions. These are two large positive numbers, but even so, if you take mod by n at the end of doing this large computation, you'll end up with m again. Okay? Just wait, I'm going to show you an example. I promise it's going to work. But that is the idea. That's the basic idea. Okay? Any questions about this so far? There's a lot of numbers and number theory involved. I don't need you to learn it, but I just want to give you a flavor of what's happening. So, because you're eventually going to take mod n at the end of the day, you can only get back an answer that is a valid remainder by n. So any message that you send should be between 0 and n minus 1. You can't make anything bigger than that. If you need a bigger message, you need a bigger n value. And also 0 and 1 don't work very correctly because like you end up with 0 and 1 at the end, and that's easy to crack. So usually the message is never 0 or 1. But yeah, here is encryption and decryption in RSA. To encrypt a message M that you want to send to somebody, you get their public key, that E and N, and you calculate your message to the power of E, and then take mod N after that. Okay? That's called C. That's your ciphertext. And then to decrypt, you just calculate that ciphertext to the power of D, because you have your private key saved, mod N. So let me show this all to you. I'm going to use Python to do it. Give you a sneak peek of what Python is. It's just a programming language. Good for quick little math like this. Whee! So here's Python. So let's see, what message do we want to send? Let's send 42. That's the message I want to send to somebody securely. Okay? So I'm going to calculate m to the e mod n. So 42 to the 17th power mod 3233. So 42 to the 17 is this. It's a very large number. But then when I shrink it down, using mod, the percent sign, 3233, this is the encrypted message, 2557. It's very hard to decrypt if you don't know the decryption keys. So C is 2557. Looks nothing like 42 anymore. With large enough prime numbers, this is virtually uncrackable. And then to decrypt that C, it's called a ciphertext. It's an encrypted thing. You calculate C to the power of D mod n. And D is pretty big, so 2557 Let's do it. 2557 to the power of 413. That number can't even fit on this window. So it's this. First you calculate that, huge, and then you take the modulus by 3233, part of your public key. And miraculously, due to some very fancy math, you end up with the message that was intended for you. There's the 42. Isn't that cool? So definitely read up about this if you're interested. I'd be happy to talk to you more about it. It is alive and well still, RSA. So that gives me M again. Any questions about that? Again, I don't need you to understand, or I don't want you to memorize this process. I'm not going to test you on, okay, here's E, N, and D. Please encrypt and decrypt this message. I just want you to understand it at a higher level. All right. Yeah. Now we can ask the question, is it ethical to use encryption to send messages to other people across the internet? So let's debate this. So I have a question for you. So let's get into our peer instruction groups. You know what group number you are, and I want you to debate the following question, okay? I will split you up into groups, for and against again. I'm going to force you to think a certain way. So let's say that, first of all, let's go there. Are we all done with attendance, by the way? Can I stop that? All right. So let's go to the written nice page, please, and I'll clear it out for us. And then I want you to come up with 2 arguments for your group. And you can put them anywhere you want on your group's line. So let's say if you're an even-numbered group, then you are for encryption being used when you're sending messages across the internet. If you're an odd-numbered group, you're against encryption. All right? So please write 2 arguments. Try to get 2 good arguments as a group. Write them down on that page in support of whatever stance I just gave you. Okay? And then we'll come back, we'll talk about them, and then together we'll figure out, like, okay, what would have Kant said? What would have Mills said about these things? And that will lead us well into the final topic of the day. Okay? Any questions about that? So yeah, go forth. Go come up with some good arguments. I'll give you like 4 minutes or so. Is it ethical? Should we be using encryption? Think about this from every point of view. Like your point of view as the sender, as the receiver, as somebody else who might law enforcement, all that stuff. Take about one more minute to get in your two ideas. All right, that's my timer. Let's come back. Let's see what we're thinking. Hopefully that was enough time to get some good arguments in. Let's see, where do I want to be here? So very nice. All right, let's take a look. Let's take a look at some even groups who are for encryption, some odd groups against encryption. So, it's moral because everyone has a right to have private conversation. Okay, so kind of like going back to natural rights, like we are kind of born with this idea maybe. We should always be allowed to have private conversation with other people if we choose to. Nobody should take that away from us. That's definitely one of those kinds of rights. Let's see what group 8 is thinking. Privacy, yeah. Paramount. No one needs to know what I ordered for lunch. It's kind of like a question of who needs to know, maybe. I like that idea. Yeah. Privacy is good. You don't want other people knowing your information. So there's always the idea of there's a malicious party that you could always think about, right? The person that, what would they do if they got my credit card number, if they got my bank account information, if they knew what I was trying to tell my significant other, all those things. So that's no fun. Were we all even groups today? Did we all just change computers so that we could be even groups? It looks like it. That's okay. So let's think about the other side. Why might you be against encryption? The one that comes to my mind would be like law enforcement. It's if you do something bad and you cover your tracks really well with encryption, law enforcement cannot decrypt your messages that they could use to convict you with. Right? That is potentially a large issue. Because otherwise, some bad person who sent a lot of encrypted messages and like that was the smoking gun evidence, if only we could decrypt. You can't do it. You would need billions of years on a supercomputer, and we just won't get there during that person's lifetime. So that's the easiest thing that I can think about. Yeah. So let's ask Kant and Mill. I think Kant is all about privacy, first of all. So he would probably say, yes, we should totally always use encryption. Private info should remain private. I should get to choose. Everyone should always get to choose who gets to hear what they're trying to say. I think Kant would be a proponent of privacy, of encryption. Should remain. Just because I'm telling my bank account number so they can look it up, doesn't mean I should be telling my neighbor that. Yeah? Or the person sitting next to me at the stoplight. There's no need. It's an easy answer from Kant, I think. And then for Mill, for utilitarians, you'd have to weigh it, right? You'd have to be like, all right, on one side you get a lot from privacy. Privacy is good, right? Encryption allows us to remain private. Privacy is a good thing to want to have. We should hopefully have a right to that, yes. But maybe it's a bit harder to protect people, to enforce the law, to protect people from harm, maybe. Those kinds of things. Like if a bad person was using encrypted messaging to stage some kind of bad act, right? Think of that. Protect people from harm. It would be a lot easier for law enforcement to protect people if everybody's conversation was always known to them. But that takes away from your privacy, so you have to weigh that if you're writing an essay about this stuff, right? So those are my ideas there. Are there any questions about this? It's a fun little topic to think about, I think. I have one last subsection and then an essay for you. Okay, a new essay for you. 3 topics, very similar to one another. Let's go through them. So first we have Chelsea Manning, who back in 2010, she gave WikiLeaks, a very notorious website that you've surely heard of by now. Definitely look it up if you haven't. She gave WikiLeaks almost 1 million classified or very close to being classified documents from the military and just diplomats across the U.S. or the world, who are U.S. diplomats, by the way. And first of all, this is crazy, right? If you were trying to leak this before, if you were going to be a whistleblower back in the day, to be able to access 1 million documents, to be able to photocopy them, would have been impossible. So this is like inconceivable, this kind of leak before the information age. But Chelsea Manning thought that this was a good idea, so she leaked these documents. And I think, if I remember correctly, they all had to do with like civilian deaths or issues with the wars in Afghanistan and Iraq. Like the U.S. was hiding the fact that a lot of civilians were getting hurt, and so Chelsea Manning brought these ideas to light. And so she thought it was best to blow the whistle like this and to just give all this information out to people. So, because this was classified information, she was sentenced to 35 years in prison, but that got commuted by President Obama, and now she's on Twitter. She's out, safe, everything's fine. So the question here is, does the value of informing the public of something potentially horrendous, like what was going on, does that outweigh the value of confidentiality? So all these documents, they were classified. She broke the law by releasing them, so was it still right to do, though? This is an ethical question. Cool. Because there's a flip side. There's 2 sides to this. There's a line, and you have to figure out which side of the line you're on. So on one side, confidentiality protects people. WikiLeaks is notorious for not blurring out the lines of files that they should have blurred out. Like, I'm sure there were a lot of names that were publicly said that were inside of these documents. And that, if people are angry about these things that have been leaked and they see those names, they might go and attack that person. That's not good. So that's one side. And then also, maybe it's a good thing to have this kind of leak because that gives more information. More info for voters and activists. Maybe you can vote out the people who allowed this kind of thing to happen. That kind of idea. Okay? So that's Chelsea Manning. I don't think I have enough time for the Panama Papers, but feel free to look into them if you'd like, because I would like to talk about Edward Snowden for the last bit of the day, because that's going to be what your essay is about. So Edward Snowden, he was a contractor for the NSA. He leaked a bunch of documents showing that the NSA was spying on U.S. citizens. They had a bunch of backdoors in like Facebook, Google, all those things. And he leaked a lot of classified information about those spying practices that the NSA was doing. It was all classified. So against the law to leak all this stuff. But he leaked it anyway because he thought that it was good to inform the public about this. Okay? All these things that were thought to be encrypted were not really encrypted. And so the NSA captured a lot of information that it was not legally allowed to capture. Not good. So the NSA was breaking the law. Snowden released these documents, these classified documents, showing that they broke the law. But to leak a classified document is itself breaking the law. So ethical dilemma here. He was on one side of it. He was indicted for espionage, and as far as I know, he is currently living in Russia with his wife, because if he leaves Russia, and goes to any country that has a deal with the US, they will extradite him and try him here. They will bring him back and send him to jail because he broke the law. So that's Edward Snowden. That's his story. Definitely go look him up if you haven't heard a lot about him, because he's the person I would like you to write about next. And this will be another 2-week essay, due week 6. It'll be 500 words in the middle, okay? So here's what I want you to write about. Here's my question for you. I got 3 minutes to explain it to you before class ends. So here's my prompt. I want you to answer this prompt question. Was it right for Snowden to blow the whistle on the NSA? He was a whistleblower. He gave all this classified information up to show that the NSA was doing a bad thing. But in itself, showing that information, like disseminating that information, that classified stuff, that was also illegal. So that's the first question. Second question, do we have a right to privacy on a public utility like the internet? Because that's what it is. Everybody has a right to be on the internet these days. It's a public utility like a phone. Because after all, like PG&E, we're all getting power bills. They're monitoring exactly how much power we're using, and nobody really cares about that. Why is the internet so different? So please answer both of those questions to me, please, in about 500 words. So that is your prompt, and you're allowed to take a stance, or you can just say, like, I don't like either stance. There's no yes or no answer, and here's why. You can tell me whatever you want, but I want you to, regardless of your stance or lack of stance, please mention both sides of the argument, because that's how you write a good argument. You have to knock down the other side or prop up your side, and vice versa. You better mention both sides of the argument and argue in favor of or against them. Okay? You might want to talk about Kantianism or utilitarianism. That might help you a lot, but you're not required to. You don't have to. Your last requirement is that you better cite one source. This is your first citation requirement. So please find a good source on the internet or in the library and cite it in your essay. Okay, so 500 words, answer the prompt, cite a source. That is all I have. Are there any questions about that assignment? Should be a pretty quick essay, only 500 words. And yeah, that's all I have for you.